Show that lambda is an eigenvalue of matrix A and find a basis for the eigenspace. Use this basis to find one vector x that corresponds to this eigenvalue. So here we have a beautiful 3 by 3 matrix A, and our eigenvalue, lambda equals 7. So in order to show that lambda equals 7 is an eigenvalue of matrix A, we need to show that the equation matrix A times vector x equals 7 times vector x has a non-trivial solution. Then to find the basis for this eigenspace, we're going to need to row reduce this matrix equation to its row reduced echelon form and find a general solution for x. So to begin, the very first thing that we need to do is rewrite this matrix equation. So we have a matrix A times vector x is equal to 7 times vector x, and bringing all the terms to the left-hand side, we are left with a matrix A times vector x minus 7 times vector x is equal to the 0 vector. So notice that we have this common vector x. So when we go ahead and pull that out, we are left with matrix A minus 7 times the identity matrix, and specifically the 3 by 3 identity matrix, multiplied by vector x is equal to the 0 vector. Now, this is something that we can work with. We can see that we have our matrix A minus 7 times that 3 by 3 identity. So let's now go ahead and find this matrix. So we have matrix A minus 7 times that 3 by 3 identity. So matrix A, we have 8, 1, 4, 1, 6, 2, negative 1, 1, 5. And then I'm going to rewrite minus 7 times the 3 by 3 identity as plus the 3 by 3 matrix, negative 7, 0, 0, 0, negative 7, 0, 0, 0, negative 7. And we are now ready to go ahead and combine up those like terms. So 8 minus 7 is 1, 1 plus 0 is 1, negative 1 plus 0 is negative 1. Second row is 1 plus 0 is 1, 6 minus 7 is minus 1, 1 plus 0 is 1. Third row, 4 plus 0 is 4, 2 plus 0 is 2, 5 minus 7 is negative 2. Beautiful! So now that we have this 3 by 3 matrix, we are officially ready to start row reducing this matrix augmented with the 0 vector to its row reduced echelon form. So here we go. We have our augmented matrix, matrix A, minus 7 times that 3 by 3 identity, augmented with the 0 vector. So taking that matrix we just found, we are ready to start row reducing. So beginning with the first pivot position, we want to use this pivot to eliminate the entries below it. So we can do this by doing minus the first row plus the second row, and then minus 4 times first row plus the third row. And let's give ourselves just a little bit more room. So we can see our first row is going to remain as it is. That's still 1, 1, negative 1. The second row, we have negative 1 plus 1 is 0. Negative 1 minus 1 is negative 2. Negative times a negative, so we have positive 1 plus 1 is 2. Now for the third row, we have negative 4 plus 4 is 0. Negative 4 plus 2 is minus 2. And then positive 4 minus 2 is positive 2. So let's pause for a cause here real quick. And what do you observe about this reduced matrix? We can see a linear dependence relationship amongst the column vectors. Notice that column vector 2 and 3 are dependent on each other. They're scalar multiples. Right? This means that a free variable exists. Woohoo! So we know that lambda equals 7 is going to be an eigenvalue of matrix A because a free variable exists, so this matrix equation has a non-trivial solution. Now, we know that we also want to find an eigenspace for this lambda. So let's continue row reducing. So starting with our second pivot position, we want to eliminate the entry above and below it. So we can do this by doing 1/2 multiplied by the second row plus the first row. We could do a scalar multiple of negative 1/2 times the second row. And then we can also do minus the second row plus the third row. And so this is leaving us with, the first row is 1, 0, 0. Our second row is 0, 1, negative 1. And our third row is all zeros, confirming our observation that a free variable exists. Specifically, x sub 3 here is a free variable, telling us that this matrix equation has a non-trivial solution. So let's note here, we can rewrite this row-reduced echelon form of the matrix as a system of linear equations. We can see here that x sub 1 is equal to 0. We can see that x sub 2 is equal to x sub 3. And we know that x sub 3 is free. So using this system of linear equations, we can now write the general solution for vector x. We know that vector x is a vector in R3, where x sub 1 is 0, where x sub 2 is equal to x sub 3, and where x sub 3 is free, so it's just itself. So notice in this vector, we have a scalar multiple of x sub 3. So we can pull that x sub 3 out in front. So we have x sub 3 multiplied by the vector 0, 1, 1. And again, this is such that x sub 3 is free. Woohoo! So we are officially ready at this point to make our conclusions. So we can conclude that therefore, since matrix A times vector x being equal to 7 times vector x has a non-trivial solution, x sub 3 is a free variable, so we know there are infinitely many solutions to this equation. So since a non-trivial solution exists, we can conclude that lambda equals 7 is an eigenvalue of matrix A. Now, this question also asks us to identify a basis for the eigenspace. So using this general solution, we can say that therefore the eigenspace E sub 7 is equal to the set of all scalar multiples t times the vector 0, 1, 1. Now remember, alternatively, we can write this eigenspace as the spanning set. So this is the span of the vector 0, 1, 1. Beautiful. Now the last thing this question asks us is to identify a specific eigenvector for this eigenspace. And now notice, looking at our eigenspace, we can see one vector standing out, 0, 1, 1. So we are able to conclude here that one eigenvector that corresponds to lambda equals 7 is vector x with the components 0, 1, 1. Now, this is not an exclusive answer. This is simply the easiest answer. We want to keep in mind, based off of our eigenspace, we can see that any scalar multiple of the vector 0, 1, 1 works here. Again, this spanning vector is simply the easiest solution to see.